Happy Friday. You guys. You're blending in with the chair, is that what you said?
Snow.
Oh, the snow. Yeah, happy spring. Okay, let's see. Your test results, I got them back and posted them last night after they sent them to me. So you can see your score online. The average was a C, which that's what C means, so I guess we're right on point. There were many A's, more B's, most B's, and then of course there were C's and D's and F's. So that's on there again for those of you that choose to retake it. Yes, as with the other exams, those of you that took the exam, it's a retake. So if you took it, you can retake it if you choose. And it's not closed until Sunday night, like past ones. So yes. I have also made available the next homework assignment. We are starting units, well, I don't know if it's a unit, part 4 in the book on sound. Chapters 19, 20, and 21, which are on the WebAssign calendar and in the resources, the class schedule. It's been on there since the beginning of class. You can always go there and see what we're covering, where we're at. So I will start chapter 19 today. I suspect I will get through chapters 19 and 20 through next week. And I might start 21 at the end. There's 3 chapters. I won't get through enough today to assign a homework, so you have no homework due this weekend. You can focus just on the makeup retake of the exam if you want. Next week, though, we'll finish 19 and 20, so you'll have questions over 19 and 20 due the following Sunday, like normal. But you can start on those now. One warning, and I'll try to remind you next week, you'll have a second homework assignment on chapter 21. It's going to be shorter because it's going to fall on a Monday when we start chapter 21. Is that right? Didn't bring my schedule. I think so. And then we review on Wednesday and have a test that Friday in 2 weeks. So you don't have a weekend to cover on chapter 21. The reason I'm telling you is I'm going to make that assignment available before this homework assignment is due. That makes sense? So you're working on chapters 19 and 20 now. It'll be due not this Sunday, but next Sunday. This is all on the schedule. But you can start looking at chapter 21 ahead of time, because some of you will feel like you have less time, even though I can tell most of you wait till the day before. And it will be due right before class that Wednesday when we start reviewing. So hopefully I'll remind you well that Monday when we start chapter 21, so it's a little different. And superhero paper, that's the instructions. Friendly reminder, you have, is it 2 weeks now? It's due anytime up through April 1st. I strongly encourage you, even if you've done it before, reread the instructions and the rules and important things to keep in mind. I'm pretty sure I got it all here. If you're confused, of course, ask me. Because this is what I'm grading on. This is what I'm holding you to. If you overlook something because, oh, I forgot I was supposed to do that. Well, it's right here. I don't want you to miss points just because you didn't read the instructions well. So if you've been working on it, great. Reread it and it can help you. Oh, yeah, I forgot a works cited. I need to include that. Also, it's kind of at the end. Everybody doesn't read to the end. I said, I would like you to turn in your paper in printed form as well as electronically. So you'll submit 2 forms. I want it in writing. You can print it off and email me or bring in a stick, however. Get me a digital copy also. A lot of people overlook that. Any questions on the paper at this point? How many are done? Again, though, you don't have to wait till April 1st. Okay. Vibrations and waves, chapter 20. I like how he starts it. Good vibrations. Beach Boys song. What's a vibration? Well, how would you define a vibration? An oscillation in air. Does it have to be in air? No, an oscillation. I like that. Something that oscillates back and forth. I like fun terms. My wife teaches preschool, so I aim for a lower vocab when I can get away with it. And so, like the author, that's why I like him. He uses wiggle. A wiggle. So those molecules we've been discussing a lot, one of their motions is wiggling, oscillate back and forth. Those three types of vibration, well, you got that rotational. So if it's rotating back and forth, that's an oscillation, it's vibrating. It can also, this doesn't work that well, but vibrational, that's oscillating. Those are vibrations. It's wiggling. It's a wiggle in time. A wiggle in time. A certain amount of time. So here's my wiggle in time. I'm pretty proud of this. Kind of clues it together. This is an ultraviolet laser pointer. Ultraviolet. Let's do dimmer here. And so I just have it reflecting onto the screen here. If I nudge it, it's vibrating. That's a vibration. It's wiggling in time. Up, down, up, down, up, down, back and forth, up and down, over and out, side to side. Okay. So vibrations are key to sound. Everything starts with a vibration. Well, that's a wiggle in time. What do you think will happen if I move this phosphorescent sheet in front of it? It makes it glow in the dark. And you just get up and down, and then that thing doesn't swing very straight, so it kind of goes in a circle too. Circular motion is a vibration. It cycles once around, twice around, 3 times around, back and forth. It's periodic. It repeats. It's repetitive. Vibration wiggle. Well, let's whack it again. Now, I will move the glow-in-the-dark screen past the vibration, the wiggle in time. So we'll get a wiggle in time and in space. So it'll change in time as well as location. And you get a sine wave to show the periodic motion. You can go back. If I move space faster, can you see a difference? I can't see you nodding, so somebody shout something out. If I move really fast, the waves become longer. Is this changing the rate that it wiggles or vibrates? Say something, I can't see it. No, yeah, we're going to call that frequency. The rate at which something vibrates is the frequency. How fast it goes up and down. 1, 2, 3, 4. It's about once every second. One cycle, one complete repetition in a second. 1, 2, 3, 4. It gets back to the top. So we call that frequency. A cycle per second is a frequency. The wave it makes in space gives you an idea of how far it can travel in that given amount of time. The time it takes to go up and down once, it can cover a certain distance in space. And that length is called a wavelength. a wavelength. It's the distance from one bump to another, if you will. We'll redraw this. Let's turn the lights back on for us. Sorry.
So if the light was moving faster, we'd get a faster sine wave?
Yes. If the light was vibrating faster, we'd say it has a higher frequency, and you'd get the wiggles quicker. So for the same motion across the board, they would look closer together because they move up and down more quickly. The three I did, that was swinging at the same rate, the same frequency. But if the speed of the space that it travels changes, you saw the wavelength changed. We're going to define that relationship. And we'll use an equation to guide our thinking. Chalk. So, a vibration. Wiggle in time. A wave is a wiggle in time and space. Oh, and I didn't write it. Technically, these are periodic wiggles, ones that repeat. Sound, we call a mechanical wave because it propagates the vibrations through a material. Sound must go through something, through the metal, through the air, or through water, and it vibrates the material. Light is more a pure energy wave. It doesn't need material. Remember our heat transfers, radiation? That's an electromagnetic wave that looks, like that. It can oscillate on its own. It doesn't need a medium. That's like light, electromagnetism, electromagnetic wave. Sound, on the other hand, is mechanical and needs a material to go through. But the key to all waves, whether it's sound, light, earthquake waves, water waves, heartbeats, all of them, the source needs to be vibrating. The vibration is the key there. So you get a sine curve, and that's representing a wave in time and in space. We call this distance, let's do it bigger. Helps me draw it a little more to scale. All right, so we call this distance a wavelength. That's a wavelength. We'll call it W in this class. Most in physics they use lambda, but mainly because it won't let me do lambda and WebAssign. I'll just use a W. That's the distance. When it's up, it travels down and back up. It's made one complete cycle in time there. But it's covered that much distance. So that's a distance. Standard unit of meters, a wavelength. This is also a wavelength. We call these bumps crests. Crests. That's a crest, that's a crest, that's a crest. And we call the ones underneath troughs. Trough, trough. I like bumps, up bump, down bump, but crest, trough. You can also, what if we start at this point right here, point X. When do we get back to X? In the cycle. Tell me when. You ready? So every time it crosses this line, which we want to give a name, equilibrium position, or, oh, I'm so sorry. Squeaked the chalk. Midpoint. Every time it crosses the equilibrium position, It's back to its home base. So it does cross here, but that's not repeating in the cycle. It's only done half of its cycle. It's gone up and back to there, but now it goes the other way and back. Or think of direction. Remember vectors? Here we're going up. From this point, we start going up. We get here back to the same position in space, but we're now going down. So we keep going. And over here, now we're back to the same position in space and heading up. So that distance is also a wavelength. Can you see that? If I drew it to scale, they're all the same length. You can actually pick any point. How about this point right here? That would go to right there. And that'd be a wavelength. Does that make sense? Now that I've drawn on that one enough. Amplitude, we call this distance. It's the maximum displacement from the equilibrium position. Doesn't that sound good? The maximum displacement from the equilibrium position. The size of the wiggle. That's how far the thing moves. But it's up or down. It's the same amplitude. Around the equilibrium position, it oscillates so far this way, so far that way. This is an amplitude on one side, and so is the other side. So here also. The time it takes to complete one cycle, so in this case from X to Y, we call a period. They give that the symbol big T because it's time. So that's the time for one cycle. It's in seconds. You can just count it. Like I was doing, 1001, 1002, 1003, 1004. We'd say the period is 1 second. It takes 1 second to complete a cycle. And then frequency, we already mentioned. That's F. And it's the rate of vibration. So that one would be measured in cycles per second. How many times it goes around once, or how long it takes. That is often abbreviated as hertz. Let's say right as Hz. Raise your hand if you've never heard of hertz. Only one. Hey, that's pretty good. Well, hertz is just a term. It's a guy's last name. It's the unit for frequency, and it means cycles per second. So, example. Rachel, what's your favorite radio station? 89.1? 89.1. Do you happen to know the units? Megahertz. That's 1,000,000 hertz. So what that means is the wave that it transmits on, its carrier wave, it's an electromagnetic wave, it vibrates like those, is vibrating up and down 89.1 million times a second. Cycles per second, but this one's millions of cycles per second. So 89.1 million times a second. That's fast. So that's what hertz is. You got an AM station? Let's see. About 1010. I don't know if that's one here. I just one I got in my head. That's in. Look on your radio dial next time. Of course, I guess getting away from radios. They don't have the dials, do they? That's in kilohertz. That's 1,000 hertz. So faster or slower? Yeah, this is FM. This is AM. Yeah, that's slower. So the carrier wave that transmits the information vibrates more slowly.
What about
XM? On the
like Sirius radio, the new radio?
Yes.
My car has it.
You know, that's a good question. XM, I don't know the frequency range. It's still in radio band, so we're still up here in the thousands and millions of hertz, but I don't know what specific ones. I need to look that up. You think it's what? XM is purely satellite, not radio waves? Yeah, obviously, I don't have this in my car. Mine still takes audio cassettes, sorry. I'm proud, though. It's the same stereo I put in when I was in high school. It's still kicking. The car hasn't. I've been through 3 cars, but yeah, whatever. So it's satellite. Well, then that tells us it travels at the speed of light, which is, oh boy, 3 times 10 to the 8th meters per second. That's the speed. The frequency varies depending on whether it's what type of wave it is. But that's the wave speed. These are electromagnetic waves. They travel at the speed of light, but they vibrate at different rates. So I still don't know the rate for XM. Research it. If I forget, I'll try to remember Monday, and you guys too, and we'll bring it up. But that's vibrations. A neat relationship here between frequency and period. Please note this. They're inversely proportional to each other. It's a real easy way to go from one to another. The simple example here, this seemed to oscillate at about once a second, right? 1, 2, 3, 4, 5, 6. So the period is 1 second. What's the frequency? 1 cycle per second. What if let's choose something different. This is different, I know. Okay, we'll start at this point, over here. Right now. Right now. 1001, 1002, 1003, 1004, 1005, 1006, roughly. So that the period is roughly what? Ready, go. 1001, 1002, 1001, 1002, 1001, 1002. What's the period? 2 seconds, because that's the time it takes to repeat one cycle. So if the period was 2 seconds, the frequency is the inverse of that. We'd say it's a half a hertz. It completes half a cycle in 1 second. And you see that. 1001, 1002, 1001, 1002. It's halfway done. So that's how those two play. And then the relationship between, let's write that down, wave speed. We're going to use v because it's a velocity, is the frequency times the wavelength. And hopefully somebody's noticed by now, I found this shirt. It's a little chalkboard you can draw on. And I can wipe it off, clean it off with water and do it again. So you can see my pink wave. You can see the wavelength from crest to crest or trough to trough. You see the amplitudes, distance, maximum distance from the equilibrium position, the blue line. Here's how frequency and period relate. They're inversely proportional because frequency is cycles per second. The second's in the denominator. That's how I remember. And then the equation I just wrote, the wave speed is equal to frequency times the wavelength. So how fast the wave seems to travel. For what we've done thus far, that's like how fast that space was moving. How much distance it was covering in a certain time. You know velocity, distance, and time. Let's write that again. Before, velocity was distance over time, right? It still is. Wavelength is a distance, right? Covers a certain distance. In how much time? Well, frequency is 1 over the time. So you get distance over time. So it's nothing really new. We're calling distances and times now wavelength and frequency so that we can relate them to waves. And that wave speed was how fast the space was moving, either past the vibration or the vibration through space. Tells you how fast it's traveling. So, again, electromagnetic waves in space travel really fast. Whereas these waves are a lot slower. Sound waves, go ahead and give you a sound. Give you an idea. The speed of sound in air is 340 meters per second. That's how fast any vibration can travel through air. Do you think it travels faster or slower in water, the same sound? It's actually faster. How about in metal? Faster. Yeah. It's a mechanical wave, sound is, and it has to make the material vibrate. The material itself is what's actually wiggling. Let me show that a little better. Let's do that with this first. Well, here, you can make a wave. I'll make a pulse. And you can see the pulse travel and reflect back. The individual bars don't move left and right. This bar right here, you can look at this one in the middle. Watch it as the wave travels through it. What's it do? Which direction does it move? It's moving vertically. It goes up and down. It can vibrate. If I keep doing this, you can see the individual bars just go up and down, up and down. It vibrates. But the wave is propagating through the medium. The wave isn't the material moving itself. The material stays put and just oscillates where it's at, like a vibration. But the wave propagates through the material. You're all looking at me like, duh, but that's an essential point. And remember that when you're thinking of some of these problems. Let me see. What did I write? Through wave motion, energy can be transferred from a source to a receiver without the transfer of matter between the points. So if I want to send some information or energy from this side to that side, I don't have to take this and throw it over there, physically move it. I can use a wave to propagate it over there. And there it is. Now it's over here. That's what a wave does. That's how you get your radio signal. The radio station transmits it, but that wave doesn't, like this little pulse, doesn't come to your car. That air, those electrons aren't just zipping through space. They cause ones to oscillate, which then hit their neighbors and make them oscillate, kind of like a domino effect. So the individual vibration frequency can be different than the wave speed. The carrier wave actually gets to you really fast, but not the individual little electrons. Lower specific heats. There is a connection, and it's more to do with but they both have to do with the molecular structure and electron structure, how well it's bound. And like for metals, as an example, sound travels pretty quickly because they're rigid. Think about it. If I bumped into you and you're bound tightly and rigid, you're going to eventually, because I hit you, run into your neighbor. How fast you do that determines how fast the wave travels through you. So in a material like metal, you can bump into your neighbor quickly because they're kind of more rigid. You hit one and they're all kind of knocked together. Whereas in air, you know, I talk, oh, and I make these airs wiggle. Well, they're not right next to their neighbors. So it takes a little time for them to get to them and knock them and transmit. That's a general principle with those, how a wave transmits. So that's why in water, air or sound travels faster. Because the water molecules, it's a liquid, and they're closer together.
You take a sound and put it into, I'm guessing, how does a radio tower work?
How does a radio tower work? Yeah, it's fun. They basically have an antenna. Oh, that way. Huh. For simplicity, just use a pole, because that works. They send electricity. They put an electric field on it, and they make electrons, or charges, but generally electrons, oscillate, vibrate. There's your source. So it's like a battery, or it changes direction. It sends current one way, but then it flips and swings it the other way. AC current makes it alternate, the electric field. And you'll get little electrons, let's say, moving up, but then they'll move down. And so they're vibrating at a certain frequency. Every time they do that, that change in electric field causes a magnetic field. And long story short, you get an electromagnetic wave. You get an electric field oscillating vertically, and you get a magnetic field. This is always fun. Vibrating perpendicular to that. And they travel through space. Then you got an antenna over here. And what do you think happens to the charges in the antenna when this vibration gets to it? Makes them start oscillating at the same rate. And then electronics turns that into sound, ends up making a speaker cone move back and forth to push the air so we can hear it. So you just change this frequency, and you've changed, from AM to FM, or tuned into a different station. When you tune your radio, all you're doing is saying, I want this antenna to resonate, it's another word, vibrate at that frequency, not at some other frequency. And that's through electronics. We'll talk about resonance a bit more. Let's see, am I forgetting anything important there? So again, key point, the wave what's propagated is the disturbance, not the medium. Your pulse, your wave can propagate, the vibration doesn't. Okay. I like how your book put this one. Pendulums. We did a lot of dropping of mass at the beginning. And see if you remember. Consider it a review for the final. You take two different masses and you drop them. Who hits the ground first? Thank you. Same time, because they fall at the same rate. Which one feels the greater force? The heavier one, because it's got more mass, more inertia, so it takes more force. That's why it weighs more. To make it accelerate at the same rate, but they accelerate together. So I can drop these, and it'll make a nice loud sound. So warning. Yep. Well, you can put it on an incline. Gravity is still what's pulling it down, just at a less of a value, instead of going straight. If I can release them at the same time. They still move together. It doesn't depend on mass. Pendula are the same way. This one's really heavy. It's solid brass. And this one's just a piece of rubber. A lot lighter. My point is, they have the same mass. So when I displace them from their equilibrium, this would be the equilibrium point down. Displace them. Try to release them at the same time. And they have the same period, and thus the same frequency. It doesn't depend on mass. That's important. But what do you think it does depend on for a pendulum? What could I change, you think? The speed. How would I make it go faster?
What was faster or make it vibrate faster? Whatever you want to call it.
I'd have to push it.
Yeah.
I could do that. You could drive it. But still, what restricts how long it takes to come back is the acceleration of gravity. So we could go to Jupiter or the moon, and we change the force on it. And that would change how fast, frequent it vibrates. I think I heard somebody else say something too. Let's make this one shorter. Which one do you think will vibrate faster? Yeah, so frequency and period do depend on the length. I'm going to write that relationship. So period is proportional to length. It's also inversely proportional to the acceleration of gravity, which is like that force trying to restore it back. Because when you displace this over here, why does it come back? Gravity's saying, no, come back. That and the string are pulling it back. But once it gets past the middle point, it's trying to pull it back this way, just like tossing a ball up. It comes back down. It's trying to come back to where it started. This is actually this, for those of you that want to know. What the key points I want you to know is this, and I guess we do it this way. Not proportional to mass. So when something vibrates, it does depend on its size. It does depend on the force trying to pull back on it. If you make something tighter, that pulls it back more. Or you can change gravity. But the more strongly, is that a word? If you increase gravity here, it's like you're pulling it harder, right? It's inversely. That means it's going to come back faster. The period will be smaller. So it'll actually be vibrating faster. Remember, the period and frequency are inversely proportional. But it has nothing to do with mass, that period, for a pendulum. Do that. Let's show you the overhead here. There-ish. Another connection for vibrations. Try to drive this home. This is a slinky, kind of stretched out, a coil. But I can turn a crank. I guess I'll be on this side. There we go. I can turn this crank in circular motion and make a vibration. So if I start at the top, there's one cycle, one cycle, one cycle. When I do that, 1, 2, up, 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 up. The same, I'm the source of vibration, but you can create a wave that travels through the slinky. If I mark a point on here, let's see, the midpoint would be about here. And that's called the what? Equilibrium position. Good. Amplitude would be this height. Or this height. That distance away that this wave is showing. What would a wavelength be from here to where? Say when. You're right, from crest to crest. So there's a wave. This would be a wave too. And let's mark this point also for a reference point. Watch one of those crests. I'm going to turn the handle once around. So I'm up top, and here we go. I'm back up top. How far did one of those crests move? One wavelength. Because it's the distance of one cycle. And it takes the same amount of time for me to go around once as it does to move through space. One wavelength. Let's see if I can do it at a frequency of 1 hertz. That'd be once every second, right? Let's see. 1001, 1002, 1003, 1004, 1005, 6, 7. So the period's 1 second, and it's vibrating once per second. What if I go faster? How about 2 hertz? That means I got to go around twice every second. Let's see. 1001, 1002, 1003, 1004, 1005. Do you see that it covers twice the distance? There we'd say the wave speed is greater. Because you saw it moving faster, didn't you? I hope. But what's still the same? Thank you. The wavelength. Yes. In that case, with this relationship is key. If we made it go faster, that's because I was turning faster. Or you can think of it either way. I turned faster and increased the frequency, so the wave speed went up. But we kept that the same. You can play games where you keep the frequency the same. What happens if you decrease the wavelength? But the frequency stays the same. What if you decrease the wavelength? What happens? You would decrease the wave speed. Yeah. And you're going to be playing these games in this unit with sound and with light. By the way, after 19, 20, and 21 on sound, we're going to cover light. And everything that I'm teaching you about periods, frequencies, amplitude, work for any type of wave. Sound waves, light waves, water waves, any wave. So this will be important. Another thing, when the wave speed stays the same, that would be like, oh, here's a good example. I'll just attempt to make sounds. Certain frequency. Higher frequency. So something's vibrating faster. But this is the same. Because how is sound traveling to you? Through the air. So my vocal folds are vibrating at a certain frequency. And they make the air vibrate, run into it. And the air vibrates until it gets to your eardrum. But it has to go through the medium. The medium determines how fast it can travel. So if I go la, ah, I'm not changing the medium, so they both travel at the same speed. Thus, which note has a shorter wavelength? The high one. Because it has a higher frequency, it must have a smaller wavelength. Higher frequency, shorter wavelength. They keep the same wave speed because it's traveling through air. We're going to discuss what if the sound goes from air into water. Well, now the wave speed can change. That means something over here changes also. I'll get to that. That make sense? Where are we at? Let's give you some points. Clicker time. All right, there's the session ID number. Lower right is normal. Give you a minute to enter that. And I'll ask you a few questions, see if you got this. and you can have a great weekend. You can work on your exam retake if you choose. Please at least reread the superhero instructions. Anybody need more time for the session ID number? Raise your hand. Okie doke. Polling is open. No, this is supposed to be easy. I heard somebody, is this a trick question? I just want to see if you're getting the terms mixed up, see if I was not explaining it as well as I thought. Sometimes I say things wrong accidentally. Hope not. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Frequency, 60% of you got that. So that means for 40% of you, I must have confused you. How frequently a pendulum swings to and fro. That's the rate. Frequency. Frequently. It even helps for non-English people. Frequently means the rate at which it's going back and forth. So that's the frequency. The period would be the actual time in seconds. All right? Let's do. Okay, go. If any of you are going, yeah, this lecture was redundant, it was on purpose because these terms are important. We're going to use them to refer to things now and with light. So I really I'm hoping you guys get these in your heads. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. %7% of you said C. The answer is D. So that's good. So then I'm going to specify. They're both lengths. So I'm glad of the four, you chose one of those two. When we consider how far a pendulum swings to and fro, to and fro, to and fro, we're talking about the pendulum's amplitude. That's its displacement. That's how far it's moving away from equilibrium. So that's why it's amplitude. Wavelength is the distance it travels through space when space goes by it or it's moving through space. Again, this was swinging, my laser, and it went up and down so far. That told us the amplitude of vibration, a wiggle in time. The wave, though, is in space. So as I move space past it, it made a sine wave. Then we could see how much distance it traveled in space. That's wavelength. Does that help with the distinction? Polling's open now. Oh, scratch that. I had that on my list to do. I didn't cover that. That was what I'm getting to next. That'll be the first thing. Okay, try that one instead. Go. I especially like the 8 people that voted on that last question before they even had time to read it. Maybe that's why I get 10% missing the question. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 68% of you say wavelength. Good, you got that formula down. All right. So go read chapters 19 and 20. You could be ahead of the game when we discuss it next week. Bring any good questions you might have. And have a great weekend.